So this is where we left off last time, and let's move on. So this time we are going to go into a teeny tiny bit more detail about measurements and how to measure like different objects. So okay. First of all, it's this: weight does not equal mass. This is a very important thing to know in both chemistry and physics. So mass is measured in grams, and weight is generally measured in newtons. So the mass of an object will not change, and the weight might change. For example, the mass is defined as the amount of matter in a certain object, and is measured in grams. So wherever you bring for example, like a stone, it will always uh, like have the same mass. But weight measures how much gravity pulls on that object. For example, if you bring a stone that has a certain mass to, for example, the moon, which has less gravity than Earth, then in that case, gravity is going to pull on the stone less. So the stone's weight is going to be less. And that's why a lot of astronauts weigh, less when they're on different planets. And that is the basic concept of mass and weight. And here's another concept: matter. To be matter, you have to have mass and you have to have volume. So volume means you have to take up space. Mass, we already know. Here's like a fun question. Some fun questions. Is air matter? Sure. Air are molecules. Nitrogen, oxygen, different gases, but they're generally all molecules. Or, well, yeah, all molecules. So they have mass because molecules do have mass. They're made out of atoms, which are made out of protons, neutrons, and electrons. And it also takes up space. We might think of air as empty, but try moving your hand through the air rapidly. You feel some kind of wind, right? If you're moving your hand around like that in vacuum, which is, without anything, like no air, nothing, the wind feeling won't be there. Another way to feel like how air has like mass and volume is to just use a fan and blow yourself in the face. Yeah, you will feel it. And is sound matter? Sound is not matter because, sound, we can't really say sound is a thing, but sound is like a wave of energy. In physics, there are two types of waves, basically. The longitude, the like transverse wave, which is a bit like this, and the longitudinal wave, which is a bit like this. Oops. I did not mean to do that. Okay. Let me just flick back. I accidentally hit the button on my pen, so sorry about that. Anyways, like I said, transverse waves are, actually, this is an interesting thing to learn, but are not covered transverse and longitudinal waves like in this lesson. But basically, sound is a wave. There isn't sound particles. There's no such thing. And here's a very, very interesting question that my classmates and I have been arguing over for more than 2 months. Is light matter? Simultaneously, light is matter and not matter, but I'll go into the details in another time. Antimatter cancels with matter. It has mass, but it has antiprotons, anti-electrons, and anti-neutrons. I'm too lazy to type the anti, so I just left a negative here. But electrons, first of all, are already negative. Neutrons and no charge. Protons are positive. What I mean by this negative does not represent their charge. It represents anti, the word anti. So it has antiprotons, anti-electrons, and anti-neutrons. And here's the way to calculate weight, but this is generally more on the physics side. Weight equals mass times gravity. On Earth, the gravity is about 9.8 meters per second squared, mostly. And okay, so for example, if we want to measure length, we use a ruler. Measure time, timer clock, etc. Measure volume. Here's the cool thing. So for liquids, we can use a beaker, graduated cylinder, and a lot of other flasks. But for solid, here's the interesting part. Regular solid, of course, we can just calculate. But for irregular shaped solids, we have to use the graduated cylinder. Okay, my drawing is really bad here because at the time of making this, by the way, this is my notes. So school just started back then. So by the time of making this, I don't actually have my board, which I do right now. So I'll draw it again for you guys. Assume that this is a graduated cylinder. Oh, by the way, here's a joke. Graduated cylinders have graduated from college. But like the graduated in this case just mean marked. Like marked with how high is the, like how many liters, etc. Anyways, so first of all, we put a certain amount of water in the graduated cylinder, and we read the volume of that amount of water, and then we put the object in. If it's an irregular shaped object, the water level will rise because of the addition of the object, its volume. So of course we know that V2 is going to be, volume 2 is going to be larger than volume 1, because volume 2 basically is water plus object. Volume 1 is just water. So by theory, volume 2 minus volume 1 plus water, subtract water, they cancel out, and we get the object's mass. Sorry, I mean volume, usually in milliliters. So this is a really interesting way of calculating volume. Today we're just going to go over 2 slides, and this is the second one. Here we're going to talk about reading the meniscus. Basically that's for the next slide. Actually today I'll do 3 slides. Significant figures, which is also the slide after that. But significant figures, because they're a pretty big topic, I will leave these for another video. So then we're just going to be talking about measuring and reading meniscuses. Measuring. Okay. Assume that we have a, for example, a pencil. I know this is not a pencil, but just assume that it is a pencil. So this is like a closer screenshot of like this one. We can say that it's between 12.9. This is 12, by the way, not 2. Here, 12. And this is 12.1, 2, 3, 4, 5, 6, 7, 8, 9. Or like just one before 13. So it's between 12.9 and 13.0. But we can't say 12.9. In physics, at least our physics teacher tells us that basically we can only approximate. And in physics, in this case, we do not measure, like, for example, 12.98. But in chemistry, apparently we do. So basically, we have our confident digit, which is, for example, if there's a thing, that this is like the edge of the thing, like the thing's here. This is between 1 and 2. So our confident digit is going to be 1. So we're sure that it's going to be 1 point something. But what something? Here it's approximately in the middle, so we can guess. We can like approximate. So we guess it's about 5, about 1.5. In this case, it's really close. Oh, by the way, we only need to guess 1 digit. Only 1 digit, not 2. it's sort of like 12.99, 12.98 ish, but we're confident that like it's gonna be at least more than 12.9 because this is the line for 12.9, so it's gonna be more than that, and it's very close to 13. So I guess 12.98. In this case, 12.99 would also work, and so we have to remember that. So we have to remember to guess another digit as well as have our base confident digit. There was like one very holding test question which says like it gives the measurement like this, and it says is the measurement A 12.9, B 13, C like 12.98, and or D, well, something that's not related, 13.1. And I say it's very trolling or holding, as I like to call it, because at first it's very tempting to go for 12.9, and in physics, like at least in like 6th grade physics, we are encouraged to not approximate, but in chemistry we are encouraged to approximate. So in physics, this one will be the correct answer, but because that's a chemistry test, this one is the correct answer. 12.99 would also work, and some of you might say it's actually closer to 12.99. It probably is. So here is reading meniscuses. So basically, again, forgive my drawing here. I know it's horrible. Anyways, basically this thing happens in like the test tube a lot, though it also happens in other things. Try to have like when you are like putting water in a like large container like a plate or something, you would realize that the water is a bit stuck like to the edge of the plate, like a teeny tiny bit stuck to the edge of the plate. You might like say, what about this? What about the water's about to go out, but like it's just standing out, and instead of forming a thing like this, it forms a thing like this because water. Well, there's this attraction between molecules. The molecules want to stay together, and the molecules really don't want to break. So unless the force is too strong for them to, unless the force is so strong that they have to break, they will not break. But normal meniscus, basically, if you put like water or anything except mercury in a like large container, like rather flat one. This one might actually be commonly observed, like when you're putting soup in a plate, etc. You would see that it's like sticking to the edge, and it doesn't seem weird because like still it's pretty normal. But when I first learned about the meniscus, it's weird to me. Like really, it's weird, and I've got no idea why it happens. But then it is after all when I related it to the soup in a plate thing that I found just because the thing is narrower, we observe more of the curve. I've observed the soup plate thing for like a long time, and the meniscus, I only learned that in 3rd grade. So it's like you can relate these two, and well, they're pretty similar. They follow the basic same principle, which is the attraction force between the molecules here, like in the water or any liquid, and the like edge of the container is greater than the attraction force between the molecules. As I said, so there are attraction forces between these molecules, and there are also attraction forces between this molecule and the side of the container. So this force right here is greater than this force, causing the meniscus to form. Now, how to read meniscus? Basically, we look at the tip here, the tip of the meniscus. A lot of chemistry teachers will tell you to look at the bottom of the meniscus, but mercury is the only liquid that will form this type of meniscus because their molecular attraction force is stronger than the attraction force between the molecule and the side. So practically, like mercury is the only liquid that has a convex meniscus, which is what we call this. Normal liquids will have a concave meniscus. So we read at the very bottom or at the very tip of the meniscus. For example, if here we have got say like 6 milliliters. I know this is rather impossible, but let's just assume here we've got 5 milliliters. We read the 5 milliliters, not the 6 one. And for example, here we've got 4 milliliters. We still read the 5 one. We read the tip of the meniscus. So that's pretty much it for today. I hope that you've learned a lot, and see you next time.